One of the most underrated things in mathematics is taking a leap of faith. Right? When you know how to do kind of a simpler version of a problem, and then you're confronted with a problem that takes it up a notch. Right? To have the confidence to still stand in there and say, well, I know that this one thing worked in the simpler case. Let me just try it and see what happens in the more complex case. That's kind of what I'm asking you to do here. We started by looking at what to do in the simple case of solving the equation radical v equals 10. And there, the answer was, if I want to get rid of the square root, what do I do to both sides of the equation? Just square it. Right. And here, in this example, what's different? What are some things that are different about this equation compared to the first one? The thing that makes this problem scarier than the first is that underneath this square root sign, there's not just a single variable as there was in the first example. There's a whole variable expression, right? The variable y is being multiplied by an 11. We also have subtracting 18 underneath the radical, right? So the thing underneath the radical is much more complex in the second problem than it was in the first. What's another thing that should cause us a little indigestion when we look at problem 4 that didn't happen in problem 3? Yeah, the variable shows up in two places, right? It shows up on both sides of the equation, left-hand side and right-hand side. So whatever we do is going to have to account for both occurrences of the y. But if we sort of play Pollyanna for a minute, which is a really old reference that even I'm not sure I get, if we play Pollyanna and close our eyes and imagine a perfect world, then we could easily envision that this thing underneath the square root is really just one quantity, right? So this thing underneath the square root is really just, just kind of looks like a y. And that this thing over on the left-hand side is really just a number, right? And in that perfect world, this is exactly the same as the problem that we just did. So the underlying structure of this equation is actually the same as the example we did in number 3. And so that means that our strategy is not as far-fetched as we might think. And we should just try it. By which I mean, if I want to get rid of the square root, which is, after all, our top priority here, right, because it's what we're talking about today, if I want to get rid of this square root over this quantity, what's the first thing I should do? How can I do that? Square everything. Square both sides. Square the right-hand side and square the left-hand side. And when I square the right-hand side, sure enough, the square root and the square annihilate one another. And so what then is my new right-hand side after that dust settles? What's left? After the square root and the square do their magic. Yeah, exactly. So the square root and the square are gone. I don't really need these green parentheses over here. And so what I end up with is, on the right-hand side, the square root and the square are gone, and I'm left with just 11y minus 18. And on the left-hand side, I have y squared. And so our strategy of squaring both sides of this equation worked. It got rid of the square root, right? And it left us with now an equation that still has the problem of having y's on both sides. But at least now it no longer has the problem that the 11y minus 18, this binomial on the right-hand side, is trapped underneath the radical and is grouped together in a way that we're not going to be able to isolate the y. So now we're in a much better situation. But we still now have an equation that is in need of a solution. When did we talk about how to solve these kinds of equations? What kind of equation is this? What kind of a name do we give to this type of equation? Remember, in our master strategy for solving equations, when there are variables going on both sides of the equation, what's our strategy tell us to do? Yeah, we gotta combine them. We got to get all the terms onto one side of the equation, right? So what's our tool? How do we do that? If I want this 11y here, for example, to be on the left side instead of the right side, what should I do? Subtract it. Subtract 11y from both sides. And likewise with this minus 18, if I want to get that to move over to the left, what should I do? Add it. Add 18 to both sides. And after I do all of those things, my left-hand side is y squared minus 11y plus 18. What's my right-hand side? Zero. And this is the form in which we usually encounter, in their simplest way anyway, this is the form in which we usually encounter equations like this one. What do we call them? We talked about these on Monday. I've got an equation with 3 terms. Yeah, and the highest order of those terms is a second degree exponent. So we call it a quadratic trinomial. Yeah. So now I've got a quadratic trinomial in an equation where the other side of the equation is 0. We know how to solve these. We did an example on Monday, and we also did an example or two in our first run through the course material. What's our best choice? What should I try to do to this equation to get closer to solving for y? Having that 0 on the right-hand side is a big clue. Right? And it's a clue that tells us if I can factor this left-hand side, then because the right-hand side is 0, I can split apart those two factors and solve 2 much simpler equations to determine y. So that's our strategy. We want to factor y squared minus 11y plus 18. And after we factored it, we'll be able to split it apart and solve each of the individual pieces. So then we keep moving the goalposts in this problem. Now we have the question, how do I factor y squared minus 11y plus 18? And this is another thing we talked about on Monday. How does y squared factor? Y times y. And that gets us started over here, right? So y times y. What are some ways that the number 18 factors? 9 and 2. And is 9 and 2 going to be the combination that we want here? What's going to happen when I combine all my like terms in this group? Right, so that's going to give me positive 11y. And what we want is negative 11y, so how should I fix that?
Negative.
Which one should be negative? Both of them should be negative, right. If I make it negative 9 and negative 2, then their product is still positive 18. Remember, negative times negative gives us positive. But now their sum is going to be negative 9 plus negative 2. And that's going to give me negative 11. So yeah, y minus 9, y minus 2 is a factorization for this polynomial on the left, y squared minus 11y plus 18. And because the right-hand side is 0, again, that's super important, that's what allows me to then split this equation into 2 pieces. The first piece, the y minus 9, gets its own equal to 0. And the second piece, the y minus 2 gets its own equal to 0. And then I can solve each of those 2 equations in one step, adding 9 to both sides of the equation on the left and adding 2 to both sides of the equation on the right. The first step is the doozy. It's the step that freaks people out the most, right? Because you arrive at this equation, you see that square root, and you're like, ah, what do I do? Right? How do I get rid of that square root? So what's the takeaway here? What should we do to get that square root out of our equation? Square both sides. That was our first step. And once both sides are squared, then the square root symbol is gone, right? And that's great. Now it leaves us with an equation which still has 3 unlike terms in it, and 2 of them are on the opposite side of the equation from the 1. So how do we handle that when variables exist on both sides? What has always been our strategy for variables on 2 sides of the equation?
Just move them to the same side.
Yeah, move everything to one side, which we always do by addition and subtraction. So here by subtracting 11y and adding 18, now we've moved all the terms to the left-hand side, and it's given us a 0 that's super important for the process on the right-hand side. And so now the question is, how do I solve this equation, which is a quadratic equation, whose left-hand side is a trinomial. So it's a trinomial quadratic. I'm trying to solve for where it's equal to 0. But that 0 is a clue. It means that we're ready to factor. Right? If we try and use factoring to solve an equation before we have a 0 on one side, we're already sunk. Right, from step number 1. So don't even think about factoring when you're solving an equation unless you have a 0 on one side of the equation first. And so now we plug in our memory of how to factor quadratic trinomials, which came down to the question, how do I find a pair of numbers which multiply together to give me 18? And that same pair of numbers needs to add together to give me negative 11. And so we talked our way into it first by guessing 9 and 2, and then realizing that their sum was positive instead of negative 11, and then by flipping the signs on both to find out that negative 9 and negative 2 gives us the factorization we want. And now that we've got it factored correctly, we still have to solve this equation. But because the right-hand side is 0, we can split apart each of our 2 factors, give each one its own equal to 0, and then solve the simpler equations that result. So it doesn't look like a lot of work on the screen compared to some problems that we've done, but there's a lot of individual strategies that you've learned over the course of our whole semester that are all being combined together into this one problem-solving process. Right? So the more of these kinds of problems that you get practice with, you're not only, what do they call it in physical fitness? It's a compound motion, right? You're not just working one muscle group, you're working a whole bunch of muscle groups all at once, right? So you're not just building intuition for radicals, you're also repracticing your factoring, you're repracticing your equation solving strategies. You're doing a lot of things that are helping you to become stronger in other parts of the course. So as you're preparing for the exam for Monday, these are the kinds of problems, these compound movement problems are the ones that if you spend more time on those, you get a lot of mileage out of them in your learning.